Okay guys, so as promised, I'm making a video to replace the live stream we had today during all of the banging and whatnot that was going on with the windows. Okay, and let's see, let me get some colors because colored markers are good, and let's do this again. Okay, so what we're looking at, or what we're going to be looking at, what we're getting to is the derivative function, okay? And the derivative just measures the rate of change of one quantity with respect to another one. So with functions, okay, if we want to find derivatives, what we're doing is we're measuring the rate of change of a function at a particular point, at a couple of points, maybe over the entire function. So we'll get to that in a little bit. But how we start off with it is with the notion or the idea of average velocity, okay? So, as I said earlier, average velocity is just distance traveled over the time that has elapsed. So this formula right here is your formula for average velocity. And it's nice and simple because when you're given a graph, all right, you can find the average velocity over any interval that's given. And in fact, I'm going to move this for a second, and I just want to remind you of something. We know that the average velocity is equal to the slope of a secant line, right? It's the line that joins the endpoint of an interval, okay? And we know that the slope of a secant line, or any line, is just y2 minus y1 over x2 minus x1. That's the formula you learned in algebra, right? And we can also write that as delta y over delta x, the change in y over the change in x. No difference, just a different notation, okay? Which can also be written in another form. So let's just suppose we have a function here, and I'm going to just call this function f. All right, and I have a point A right here and a point B right here, okay? Now, I'm going to say that this x value, or remember, this is time and this is distance always, but you know, we refer to the t-axis as the x-axis, so we use them interchangeably. So whether you say it's, you know, when x equals, here I'm going to say x is a, or t is a, and over here I'm going to say that this is point B, x is equal to b, or t is equal to b, okay? So t is equal to a, t is equal to b, or you can say when x is equal to a, or x is equal to b, same thing, okay? This one's a little more precise because we're talking about a time axis, but it means the same thing, okay? So the idea is, you know, what are the coordinates for point A? Well, point A, if x is a, what is y, right? Well, if this is a, remember that this would be f of a. What is the function's height or function's output value? When I plug the a in, what do I get out? I get whatever f of a happens to be, right? And over here, the x coordinate is b, and if I plug a b into my function f, then, and remember, this is f of x, right? So if I plug a b in for the x here, then my output value is f of b. Again, that's just the height of the function. So another rendition of this formula, let me get my mouse cursor out of the way here. Another rendition is if I wanted to find the slope of this secant line using this notation, well, remember that, let's see, this is, this is x and this is y, and this is x and this is y, right? And if you want, you can call that y2 and x2, and you can call this x1 and y1 here. So I'm using this same formula, but now I'm using the notation instead. So I could say that this is equal to f of b minus f of a all over b minus a. Okay? All of these statements in this red box are equivalent. Shh. okay? They all mean the same thing. You're just going to see them in different ways, okay? M sub sec just refers to the slope of a secant line. That's equivalent to average velocity. If I have an xy coordinate for 2 points, then I can just pop it into the slope formula and get the answer, okay? So back to this graph here. This was a 2-hour car trip, and initially they said, well, let's compute the average velocity over the entire interval. So a secant line is going to connect the endpoints of an interval. So if my interval goes from 0 to 2, that's the entire trip, 2 hours, okay? Then what I'm going to do is connect the 2 endpoints. Well, here's the first endpoint, and there's the second one, right? And the endpoints just correspond to the leftmost value and the rightmost value of the interval. And I'm going to connect it. There's my secant line. Then what I know is that if this point is the point 290, and this point here is the point 0, 0, okay? So when I plug in a 0, I get out a 0, right? The height is 0. F of 0 is 0. When I plug in a 2, f of 2 is 90. So these y values correspond to the height of the graph, all right? It's just the height. So if I want to find the slope of this secant line, I can just say that's 90 minus 0 over 2 minus 0, which is 90 halves. And that boils down to 45 miles per hour. And the reason why I want to include my units is because my distance is in miles and my time is in hours, okay? If I wanted the average velocity over the first half of the trip, which I believe we did, well, the first half of the trip is the first hour of the trip, right? If the trip is 2 hours, then the first half is 1. So now I'm working in this interval here. And I'm going to connect this point with this point, and I'm going to compute the slope of the green secant line. Well, my coordinates have changed because when x is 1, y is 40. So the slope of the green secant line would be 40 minus 0 over 1 minus 0, or 40 miles an hour. Easy peasy. Oops, my book's in the way to the left of me, so I'm running out of room here on my desk. And likewise, if I wanted to do the second hour of the trip, for instance, well, that's too close to red. Let's use magenta. Well, then I would connect these 2 endpoints here for the second hour, and the slope of the magenta line would just be 90 minus 40 over 2 minus 1, which is 50 miles an hour. So depending on the interval that we're using, our average velocity is going to change. Just makes sense, okay? Now, so I printed out a couple of the same copies because I want to use that graph again. If I said to you, I want to know what the velocity, so I'm not saying average velocity anymore, I'm saying velocity. What is the velocity of this function, or this car, object, whatever you want to call it, at the instant when time is equal to 1? Well, number one, I don't have an interval anymore. I have a point, right? I have the point when x is equal to 1. I don't have an interval. I'm not going from 0 to 1 or 1 to 2 or 0 to 2, anything like that. It's just a point. And so the only line that passes through a single point that we know of is the tangent line, like so, right? So this is a tangent line passing through that point. And the problem we have is that in order to find the slope of a line, we need 2 points. We need, well, this one we know, right? This is 140. But we need some other point along that line, and we don't know what that is. So that's where that limit definition of the calculus comes in. So I think it's safe to say for right now that you guys are cool with average velocity, okay? That you can figure out. You've got a formula. You can definitely connect 2 endpoints of an interval and find the slope of a line. It gets a little tricky though with the instantaneous, okay? So let me make another graph. Just some random graph that I'm going to call f, some function f. Don't know what it is. I don't know what its equation is. I don't know anything other than what I see, and that's fine, okay? And let's suppose I have a point A right here, and I have another point B right here, okay? And this x coordinate is called A, okay? And then, so remember, I should have said this first, but here's the graph, right? What I want you to know is that A is here and B is here. They're super close to each other, and I'm just blowing it up here, okay? So you can see it better. Make sense? That secant line is teeny tiny in between it, right? So what we're going to do from this point A is we're going to move over some tiny little horizontal distance, which we're calling H. So I'm going to do that over here, because what I want is that x coordinate. So if I move over some teeny tiny little distance H, I have A plus the H I moved over, so that makes this A plus H, right? So the coordinates of point A are A comma f of A, right? Remember, this thing has a height. This is my function. So the height of this thing when x is equal to A is f of A. And likewise, so that's the coordinate for point A. Over here for point B, I know my x coordinate is A plus H. What's the y coordinate? Well, it's just the function evaluated at A plus H, right? So remember the other graph, it was 290 at this point, right? So when x was 2, the height of the graph was 90. Here, when x is A plus H, the height of the graph is f of A plus H. This would be my 90 here, and this would be my 2, okay? So we can easily compute the slope of the secant line using the same thing we know. We could say the average velocity, which is equal to the slope of the secant line, is equal to f of A plus H minus f of A, right? Just the change in the y's divided by the change in the x's. Now, when they change the x's, the a's are going to cancel. We have A plus H minus A, and those a's are going to cancel, so that's why we're just left with the H downstairs, okay? So back to this up here, there is one more little formula called the distance quotient. Oh my gosh, I'm tired. Difference quotient, okay, which can be written as f of A plus H minus f of A all over H. So I can add that in the box, okay? This one here is called the difference quotient. Very important little guy here, okay? And again, this A is some point in question plus some teeny tiny little distance to the right. Or it could be to the left too, but that would change the formula a little bit. Okay? So we move over this teeny tiny little horizontal distance, H for horizontal distance, and we get this x coordinate, or this x value of A plus H. So when we plug it into our function, the height is the function f of A plus H. So for right now, if that's bothering you, just memorize the formula. It'll get clearer soon. The problem is what if, I'm going to take the same graph. So here's my function f, here's my point A, here's my point B. And we can easily find the slope of that secant line. We know that the slope of the secant line, which is average velocity, is f of A plus H minus f of A all over H, right? We just determined that. So let me move this over. This is my A. This is my A plus H here. Okay. All right. Well, the question comes up for instantaneous velocity. I want to know the velocity exactly. I want to know what is the instantaneous velocity or the velocity, they mean the same thing, at x is equal to A. Not over an interval, but at a point. At the point where x is equal to A. Well, I could use this secant line to approximate it, but it's going to be way off. I mean, this almost looks like a zero slope, so my graph was not that great, but let's just pretend it's like a half or something, all right? Let's pretend it's not zero, because I can't draw. So say, how can we approximate this tangent line using the secant line? I know if we decrease the width of the interval, so remember right now, the distance from A to A plus H is H, right? This whole thing here is H. If I decrease that width by moving point B closer to point A, so maybe I'm going to move it here. Okay, so forget about that now. And I'm going to connect those two. The slope of this secant line is a better approximation of this tangent line than the original one was, right? So now my distance H goes from here to here. This is getting messy. I'm going to carry on with this. So I'm going to put A here, and I'm going to call this A. All right. Now remember, the original B was here, but we already moved it once. Well, twice, right? We moved it here and we moved it here. We want, that doesn't look like a flat line anymore, okay? So we did the blue secant line, right? We connected these two. That's not a very good approximation of that. This slope looks like maybe a 1 and this looks maybe like a 2, right? And then we tried and we moved it closer. And so maybe that's a little bit better of an approximation, but it's still not that good. And then we moved the point a little bit more to here, right? And we said, oh, that approximation's better, but it's still not even close to the slope of the tangent line. So the idea is we're going to keep moving this point closer and closer. And by moving this point closer and closer, you notice the slope of my secant lines that I draw, my colors are blending together. Maybe baby blue. Let's put one here. If I connect those, you see this little blue secant line? It almost looks exactly like the slope of the tangent line. I know that's really hard to see, and I'm sorry. I'm getting too close. The idea is, though, the important idea is this was A plus H, right? This was my distance H before, but when I moved B to this point here, when I slid it down the curve and moved it here, now this is my H, right? And then we didn't like that approximation, so we slid it down a little bit further. So now this is my H, right? And we did it again. I need another color, purple. We moved it down to here. So now this is my H, right? And then finally I did the baby blue, which is right about here. And so this is my distance H. So what's happening is I had this interval from A to A plus H, which again is really, really small. Remember, these 2 points are practically right on top of each other. We're just zooming in to make them look further away from each other. Okay, as the width of my interval decreases, it gets smaller and smaller and smaller. In other words, the distance between the 2 points gets smaller and smaller and smaller. What happens is that the secant line approaches the same slope as the tangent line. And I'm going to do this. Here's A. And here's B now, right? And here's my, so again, this is a bad tangent line. Here's my tangent line. But if I connect these two now that they're closer together, you see how this slope is almost the same as that slope? It's not quite the same slope, but it's really, really close. It's a heck of a lot closer than this slope was, right? So we're using secant lines to help us approximate what the slope of a tangent line would be. That's the whole crux of the calculus, actually. It's amazing that they could think of this stuff that many years ago. All right, and again, as this A and B get closer and closer, so if I put them a little bit closer, here's A, now here's B, and where's red? Well, I'll use this. This is my tangent line here, and look now, my secant line is practically parallel, right? The same exact slope to it. Okay, so I hope that that clarifies that. I know it gets a little bit messy when we're drawing and have all these colors and everything, but that is what our instantaneous velocity is. And for right now, since we don't really know any calculus, this is not calculus yet, what we have to realize is that we're going to be approximating the slope of the tangent line because we don't know enough calculus yet. Okay, so we say that instantaneous velocity, which is the same as velocity, is equal to the slope of the tangent line, okay, which equals to the limit as h approaches 0. Now, this h approaches 0, that means the interval width is getting smaller and is decreasing. It's getting smaller and smaller and smaller. In other words, if this width is approaching 0, that means these 2 points are like, here, let me move here. These 2 points are like this. Okay? There's practically no width in between them here, this little h. In fact, it's even smaller than that. Okay? So the width of the interval, this thing right here means when the width of the interval approaches 0, it gets so small that we can say it's 0 of the difference quotient. Now, the difference quotient without that limit notation, that's average velocity. When I throw this limit in front of it, that's the derivative. It's equal to the derivative, the first derivative, so there's one tick mark, of the function f at the point where x is equal to a. You see there's an a here, a here. That means a specific point, you know, that we want to find the instantaneous velocity at. Okay, and what I didn't say today, because I was hoping that you guys would like kind of come up with it on your own. So I wasn't trying to be mean, but I do that quite a bit to try and make you think outside the box a little bit. When I said, you know, what is the instantaneous velocity here? I'm trying to find maybe another point along this line or something like that. But what's even better than that is this. Oops. I just need another graph. Okay, so here's my point in question right here at x equals to 1. I want to know what is the velocity at the instant. And I know I can only draw a tangent line through that because there's only one point. So this is what you do. You go a little bit to the left of that point, and you go a little bit to the right of that point. Your distance has to be equal. Everything in Calc 1 is constant, all right? So for example, maybe I would say, and I always try to find convenient points because that makes our computations much easier. But, you know, if I wanted to choose, say, this point right here, I know that's like 3/4, so time is equal to 0.75, but the height I'm not quite sure of. I don't know if that's 25, 26. It's really hard to tell. And that's normal. You're going to have those struggles with these graphs. And as long as you're within, you know, a good range, like you're off by 1 or 2 digits, you're okay. All right, they'll usually accept it. But, you know, it's hard for me to tell that. So I might choose, say, this point here because I know that coordinate is 1/2 or 0.5 comma 10. And I might find the slope of this secant line. So you see the point in question, this one here with the arrow, it's my interval that I'm using here is from 0.5 to 1. That's a small interval. Is that 0.5? A quarter? Yeah, 0.5, right? That's a pretty small interval. So if I find the slope of that secant line, remembering that this is the point 140, then the slope of that blue secant line, or the average velocity on this interval, is going to be 40 minus 10 over 1 minus 1/2, or 30 over 0.5, which is 60. Okay. Now, I chose a point to the left, a convenient one, that was pretty close to the point in question. You might be saying, well, that's not really that close. Let's see what happens. That means I need to choose a point on the right that is, again, the same width. So this is my interval width, okay? So this is 1/2. So if I go over here and I go up, hey, that happens to be convenient, right? So this is equal intervals or partitions. And this is the point 1.5 comma 50. And okay, so let's try this again, shall we? I hit a button or something. I don't know what I hit, but I heard a little tap. Okay, so this is a continuation from the last one because I don't feel like redoing the video. So now let's compute the slope of this little secant line. Well, the slope of the pink secant line is 50 minus 40 divided by 1.5 minus 1, which is 10 over 0.5, or 20 miles an hour. Right? Well, that still doesn't tell me what the instantaneous velocity is. No, it doesn't. However, if you add those two values up and divide by 2, that's going to give you a really good approximation of the instantaneous velocity, because that's all you can do at this point. So let's do it. We can say that the instantaneous velocity is approximately 60 plus 20 divided by 2. That's 80 halves, or 40 miles an hour. So at this instant in time, the velocity was approximately 40 miles an hour. Now, could I get a better approximation? Sure, I could. Maybe, oh, here, I'll use this graph. Maybe, rather than choosing points so far away on the left and the right, maybe I choose these 2 points and find the slope of this secant line, and then these 2 points and find the slope of that secant line, okay? Now that's going to be tedious on this graph because, you know, I don't know what x coordinate that is. I know that this is 0.75. Maybe I could say it's 0.8. Maybe x is 0.8 and y is 30, maybe. And over here, I know x is 1.25 and y is about 47, 48, maybe. All right, so you're guesstimating these little tiny increments that are really hard to see. But again, you'd be surprised to find out that we're pretty darn accurate, even being this far away from the point in question. I'm just choosing a point on the left, right, of some interval width. So in this case, it was, you know, this is a quarter, this was a half. Then I'm choosing a point on the right, the same distance, the same interval width away, a half. Okay, I'm connecting them to the point in question. The point in question is in the middle. And I'm finding the slope of this secant line and that secant line, adding it together, divided by 2. So I'm taking the average, okay? And the average is generally a really good approximation of the instantaneous velocity. So graphically speaking, that's what we would do. Let me see. Let me get the book. Let's see what other goodies we have in here. Oh, tables are another thing. So we didn't really talk about tables today. I was going to hold off on that, but you know, this might be helpful too. Here you have a table, right? And you see we've got distance time. You see what teachers do? It's 8:52 and we're still working. So I have a table of values now. And I might want to, well, I'll just use this example because it's right here and I don't have to write it. If we want the average velocity from 0.9 to 1, that's this interval right here. My left end point of my interval is 0.9. That, remember, time is the x direction, right? And it goes to 1. So I could do f of 1, which is 40, minus f of 0.9, which is 38.76, divided by the change in x, and we get 12.4. The average velocity on this interval from 1 to 1.10 is 41.16 minus 40, change in y, over 1.10 minus 1. X. So you notice these bottom numbers are the same. That's because the width of the intervals are going to be the same. And what you get is 11.6. Okay, so you found the average velocity to the left of the point and to the right of the point. And guess what? Maybe I want the instantaneous velocity at exactly this point. All right, well, let me replicate that little chart here. I get all my graphs and things, all my paper. My desk is usually immaculate, but it's been a crazy day in more ways than one, so sorry about the shuffling. I normally don't do this that much in videos. Okay, so in that table, let me move this so I have room. Move this. So in that table, okay, I have we've got time, we've got distance, we have 0.9, we have 1, and we have 1.10. I just want to get it to focus. This camera I don't like. My husband took my better one to work. She doesn't need it. But this one I don't care for. Okay, and then the numbers here are 38.76, 40, and 41.16. Okay, so what we did was we found the average velocity on the interval from 0.9 to 1, and that was 12.4. Then we found the average velocity from 1 to 1.10, and that was 11.6. Okay, so if we want to approximate the instantaneous velocity at this instant when x or t is equal to 1, then all we have to do is add this left and right secant slope together and divide by 2. So let's do it. 12.4 plus 11.6 divided by 2, right? And what is that? 43? Is that right? Where's my calculator? Good in math, dumb in arithmetic. It's just too tedious. So 12.4 plus 11.6, right? Divided by 2. 24 divided by 2, so it's 12. So what I can say is that the instantaneous velocity is approximately 12. Capiche? Now let's look at something else. Since this number, this point in question, 1, is right in the middle of 1.10 and 0.9, what if I did this interval? This sits right in the middle. So if I did 41.16 minus 38.76 over 1.10 minus 0.90, then what I'm going to have is, in the numerator, I'm going to have 2.4, right? And 1.1 minus 0.9 is 0.2. Sorry. And if I do 2.4 divided by 0.2, I get 12. This is cute stuff. So as long as my interval widths are the same to the left and the right, and as you saw they were 0.10 on the bottom, right, for the average velocities, then all I have to do is to y2 minus y1 over x2 minus x1, and it's going to give me a really good approximation of the instantaneous velocity at time equals to whatever number is in between them. So I hope that's resonating with you guys. Let me see what else we have here. Oh, this graph here, I didn't make a copy of it, but I'll just use a pencil. This graph here is important because we can tell a lot from a graph. And there's a number of things I want you to focus on here. Okay, so we have this distance time graph. And what you see are these little tangent lines here, right? This graph here contains infinitely many points. In fact, I'm going to draw over here on the side, right here in this spot. In fact, if you have the numbers, say 1 and 2 on a graph, right? There are infinitely many numbers in between them. Or if you have the numbers 0 and 0.5, right? There are infinitely many numbers in between them. And if you have 0 and a quarter, right? There are infinitely many numbers in between them. So there are infinitely many points, right, in between any 2 points. Keep that in mind. So I could draw a tangent line to this curve at every single point in here. I mean, I have to blow this thing up massively to find every single point, which we could never really find because there are infinitely many of them. And, you know, I'm going to notice something. So maybe I'll draw a little tangent line here. Maybe I'll draw one right here. Maybe I'll draw one right here, and so forth. So at some points, these little tangent lines sort of ride along the line. This one's a flat one here. You've got this one, you've got this one, maybe I'll put one here, something like that. And what you notice is, at time 0, you're sitting in the driveway, so this is another car trip. You haven't gone anywhere. Why? Because the slope of the tangent line is flat, it's 0, right? Just like the slope of any line. Likewise up here, this tangent line is horizontal, so that means its slope is 0. So this means the object's at rest, okay? An object, when you're looking at a graph, you can tell when an object is speeding up when the slope of the tangent line to the graph at a particular point is the steepest. So here I'm in my driveway and then I start driving, right? And you notice my tangent line is, you know, I don't know, maybe that's about a half, right? And then it gets a little steeper here, and then it gets steeper here, and it starts to get a little less steep till it goes to 0. So this I know is going to be my greatest speed or velocity, because the slope of the tangent line at this point, 1.75 right here, 1 3/4, is the steepest. All right, now maybe up here it's even steeper, right? I'm not going to speculate on it, but from the interval from 0 to 1, I can say the speed is the fastest at time is equal to 1 3/4 hours, okay? At time equal to 0, I say there's 0 velocity, we're not moving. At time equals to 1.25, it's a flat line, so I'd say the vehicle or the object is at rest. Okay, so speed just tells us how fast an object's moving, whether it's a car, a plane, whatever. But velocity gives us direction. Okay, so velocity has direction involved. I don't remember. Well, yeah, let's do this number 5 because I did talk about it a little bit, but let me zoom out a little bit here. There we go. Fit it all in there. Okay, so let's just go over this number 6, and hopefully this will help kind of tie everything in together. It did it again. This thing is doing something on its own. I've never had this happen ever before. Okay, we're going to try this one last time. I've never had this happen before with this camera. I don't know what is going on, but there's some weird stuff going on at this house today. Let me say it. Maybe it's got a ghost because we removed the old window. I don't know. All right, so let's try and tie this together. So we're going to find the average velocity for the entire trip. We connect these two endpoints, right, with a secant line. And you don't really have to connect it with a line, but this is the point 2, 100. And we've got the point 0, 0 here. So if I find the slope of that secant line, it's just 100 over 2, or 50 miles per hour, right? Remove that line now. Okay, in part B, it says, find the average velocity in the second hour of the trip. Okay, well that's from hour 1 to hour 2. So again, this was 2, 100. And this is 160, it looks like. Okay, so the slope of the secant line, which is the average velocity over that half of the trip, would be 100 minus 60 over 2 minus 1, or 40 miles an hour. Okay, got 2 done. Question C, is the car slowing up or speeding down during the first half hour? Well, the first half hour goes from time is equal to 0 to time is equal to 1/2. So we're looking from, you know, here to here. Is it speeding up or slowing down? Well, think about tangent lines. If I were to draw little tiny tangent lines to this thing, are the tangent lines getting steeper? Yes, they are. So we would say it's speeding up over that interval. Then in D, that's where it gets strange, right? It says estimate the average velocity at t equals to 1. So again, they don't want the average velocity anymore. They want to know what is the velocity at the instant time equaled 1. In that split second of time, what was the velocity of the car? Well, I don't know, because if I draw a line through that, I get this tangent line, right? So what am I going to do? I'm going to choose a point to the left in a nice convenient intersected spot, and I'm going to compute the average velocity of that secant line. Now, unfortunately, well, let me change my spot because this would be the equal interval width, and I don't know what that height is. Well, let's use it. Okay, so let's go here. Okay, so this is the point 0.75 comma 40. This is the point 1 comma 60. So if I compute that slope, I'm going to have 60 minus 40, which is 20, over 1 minus 0.75 is 0.25, and that's 80 miles an hour. Okay? If I do the same here, I'm going to call this point 1.25, comma, I'm going to say it's 68. Now I'm probably going to be off a little bit. Okay, 1.25 comma 68. So if I find, I'll call this first one slope 1 and the second one slope 2. So it'd be 68 minus 60, which is 8, over 1.25 minus 1, which is 0.25. And 8 times 4 is 32 miles per hour. Right? So 20 times 4 is 80. 8 times 4, so this is a fourth, right? So you know you flip the denominator. 8 times 4 is 32. So whoa, you know, here I've got 80 miles an hour, and here I've got 32 miles an hour, which makes sense because if you drew little tangent lines, you see it's starting to slow down until it gets to a flat point, right? So the car is slowing down here, it's speeding up here. Well, if I take the average, that's 122 divided by 2. Which is 61 miles per hour. That's the approximate instantaneous velocity at the instant when time is equal to 1. How am I measuring that, or how am I approximating that? I'm finding little tiny secant lines to the left and to the right of equal interval width, and I'm taking those two, adding them up, dividing by 2 to get the approximated value. At t equals to 1.5, so let's do another one. After I do all my erasing. Here's t equals to 1.5. I don't have to do any work for that. Why? If this is what I want to know, what is the velocity the instant time is equal to 1.5, if I draw a tangent line through it, the tangent line is horizontal. That means the slope is 0. And if the slope of a tangent line is 0 to a graph, that means that the car is at rest. So I would say that the instantaneous velocity at the instant time was 1.5 is 0 miles per hour, or that it stopped. Okay? Then there's a curious problem here, which I kind of don't want to do because I want to save that for another time, but I'm going to go ahead and do it because a lot of students won't watch the video, but they wouldn't know how to answer that, but you will. So it says estimate when the instantaneous velocity of the car was the same as the average velocity. So average velocity is represented by the slope of a secant line, and instantaneous velocity is represented by the slope of a tangent line. And if average velocity is going to equal instantaneous velocity, then that means that their slopes must be the same, right? Meaning we're having parallel lines. Well, I don't know. This is for the entire trip. So if I connect these two, here's a secant line. And I'm trying to figure out, I wish I could use colors on this, but they bleed through the back and I kind of don't want to wreck the book. But I'm trying to find points along this curve that if I drew a tangent line to be parallel to this secant line. So maybe right here there'd be one, and maybe at 1 there'd be one, and maybe there'd be, right? So parallel lines have the same slope. The slope of the tangent line is equal to instantaneous velocity. The slope of the secant line is equal to average velocity. So when these when these two lines are parallel, then that means their slopes are going to be the same, which means their, the average velocity will equal the instantaneous velocity. So I think in 3 points, probably somewhere around maybe 1 and, I don't know, time equals 1.4, something like that, because here's 1.5. Maybe at time is equal to 1. And somewhere over here, maybe time is equal to 1 3/4 or 1.75. So I hope that makes sense. That was 2.1 in a nutshell. Now let me see if I can edit and piece this video together so that way I can get it uploaded so that I can go to bed. I hope you have a great night, and I'll talk to you on Thursday.